In this video, we're going to talk about antenna arrays, which is what happens when you operate a group of antennas that are identical and coherently excited. That means exactly the same frequency and a controlled phase relationship. And arranged in some sort of intentional positions. Usually they're in a regular grid of some kind, but not always. So an antenna array in practice might look like, if an antenna looks like that, it might look like this. And the reason that you do this is if you do excite these all with the same frequency and controlled phases, then the directivity of the group of antennas together is increased by a lot over the directivity of just one of these antennas alone. Then, all right, how does this work in practice and why does it work? To explain how this works, we will start with an example that just uses two antennas and then we'll generalize from that. So let's draw a coordinate system. And we'll say that there's one antenna at the origin. And that antenna at the origin, which we're naming antenna number 1, has an electric field that is some function of angle times e to the minus jk r over r. If the second antenna is identical, but we offset it by some distance, then the second antenna is going to have some other position coordinates. If we draw a second set of position coordinates that is centered around the second antenna, we call those, let's say, x prime, y prime, and z prime, then the electric field due to the second antenna is going to be the same function of theta prime, phi prime, and then it's going to have e to the minus jk r prime over r prime. Okay, but how are these things related? If you're in the far field of the array, then theta prime is approximately equal to theta, phi prime is approximately equal to phi, and 1 over r prime is approximately equal to 1 over r, because the distance between these two antennas, let's give that distance a name, let's name it d, because that distance d is much less than the distance to the observation point. But e to the minus jk r prime could be very different from e to the minus jk r, because the variation in this exponential does not decrease as r gets bigger. And it depends on small variations on the scale of a wavelength. So if r minus r prime is like around an appreciable fraction of a wavelength, then it doesn't matter how big r or r prime actually are. It's just still important because this distance is large compared to a wavelength, or even medium size compared to a wavelength. So how do we figure out what that is? We need to be more precise with what that value is. Let's look at this. I've drawn this picture for you before when I was talking about the far field, but we're going to review it again in the context of arrays. There's X, there's Y, there's Z. If we have an observation point that's off to the right somewhere, then R could be this vector, and R prime could be this vector. With this distance between R and R prime being D, what we need to do here, since these two vectors, since the observation is so far apart, these two vectors are approximately parallel. So that's point number one. Point number two is because of that, the difference in length between R and R prime is just, if you drop a perpendicular line here, it's just this little distance right there. In fact, I'll draw it in a different color so you can really see it highlighted. The difference in length that we need to know is that distance. Now this angle is theta, and since R and R prime are parallel, this angle is also theta. So the length of that little blue section, R minus R prime, is D times cosine theta. So that means that if we want to write e to the minus jk r prime in terms of R and D instead, we can do that. It's e to the minus jk r minus d cosine theta. So then the electric field from antenna number 2, this one right here, becomes the same function of angle as antenna number 1, the same e to the minus jkr over r, multiplied by a phase shift, e to the jkd cosine theta. And that's it. If you remember what we've talked about the radiation integral being a Fourier transform, you might recognize this as being a statement of the phase shift property. And you can actually go through mathematically, starting from the radiation integral, and get the same result here. So, if that's the case, then the total electric field from this array, which would be electric field from antenna number 1 plus electric field from antenna number 2 because of superposition, is just going to be equal to the element factor or the element pattern multiplied by the sum of the phase shifts for the different elements, which we call the array factor. This is another Fourier transform property, actually, because what we've done now is in physical space, we have taken one antenna element and actually convolved it with a grid of potential locations. So these can be thought of as little delta functions of specific antenna positions. So if we convolve one antenna by a grid of positions, what we end up with is a grid of that antenna at those positions in 3D space. So a convolution in 3D space, because of the Fourier transform properties, because of the fact that the radiation integral is a Fourier transform, results in multiplication in angle space, which is why you multiply the element pattern by the array factor. So that's another Fourier transform property. That's the convolution property. And in the context of antenna arrays, we call it pattern multiplication. This gets more and more useful as you add more elements to your antenna array. This is just a pair of elements. You get a cosine pattern multiplied by your individual antenna pattern. So it increases the directivity by a little bit if you line them up properly, but otherwise it doesn't do very much. But check out what happens if you have a large number of antennas here. Like, let's say we have 1, 2, 3, ... n antennas. Then the total electric field is going to be equal to that same single element pattern times e to the minus jkr over r times a sum from n equals 1 to big N of e to the jk little n minus 1 d cosine theta. This is the array factor. In this form, it doesn't tell you a whole lot. It's not super meaningful, but if you remember a single important fact from pre-calculus, then you might remember that if you have a sum of a geometric series like this, and it's finite, the result is a to the n minus 1 over a minus 1. That might not be super intuitive, but it works. You can prove it by long division. You can just say a to the n minus 1 divided by a minus 1, and what you get turns out to be, well, let's see this first. It divides into it by a to the n minus 1 times, and then you multiply a minus 1 times a to the n minus 1. You get a to the n minus a to the n minus 1. Subtract that, and you have a to the n minus 1 minus 1. So the next term is a to the n minus 2. So then you have a to the n minus 1 minus a to the n minus 2. You subtract that, end up with a to the n minus 2 minus 1, and so on. You end up with this sum of all of the terms of a. So because of that, our array factor, which we often write as just AF for array factor, turns out to be equal to e to the j big N kd cosine theta minus 1 over e to the j kd cosine theta minus 1. And if we do some factoring of exponentials, that turns out to be e to the j n kd over 2 cosine theta times sine of n kd over 2 cosine theta, all divided by e to the j kd over 2 cosine theta sine of kd over 2 cosine theta. We can move the phase reference point to the center of the array. That would just be shifting the origin to a different position. And if we do that, we eliminate this phase term, and all we're left with is the periodic sinc, in which case the array factor is sine of nkd over 2 times cosine theta divided by sine of kd over 2 cosine theta.